And with that, I'm going to ask Ed and David to turn the cameras on, and I will introduce them to you. So Ed Heinbockel is president and CEO of SavantX. He has over 30 years of hands-on experience in the management of high-tech companies and a proven record of success in building leading-edge software products in both public and private companies. A technology iconoclast since the 80s, Ed aspires to build teams around emerging technologies, from producing the first CD and DVD-ROM entertainment titles to next-gen training simulations for three-letter government agencies and the DoD. Ed notched a successful IPO and is now on his third successful startup. Ed holds an engineering degree and an MBA from Cal Poly San Luis Obispo. He was recently awarded several patents as co-inventor in enterprise search and machine learning, and most recently co-inventor on several pending quantum patents. Let me also introduce David Osby, co-founder and chief science officer. David is a prolific inventor, data scientist, and software systems designer. He is the driving force behind SavantX's advanced analytics algorithms, including a narrow AI system for enterprise search, discovery, and analysis. These algorithms are unique in the AI field as they require no data curation or training. In addition, David is heavily involved in the quantum computing field and creates simulations to test SavantX's quantum algorithms. David has architected numerous business process modeling and optimization engines over many years. He has been awarded patents and has several pending patents, and he's responsible for software design and data analysis methodologies and algorithms at SavantX. Mr. Osby attended the University of Washington. And we will get started. So at this point, I'd like to turn it over to Ed to introduce the topic.
Great, thank you, Susan, and welcome everyone. Again, Ed Heinbockel, and I'm coming to you from Wyoming. David Osby will be coming to you from New Mexico, which is where our research center is located. We're based out of Wyoming. We are excited to share our story today, and we're going to do this in the most expeditious fashion that we can. We've got a few slides to go through. David will be taking us through the meat of the process of what we've done. And I promise you no quantum word salads today. We'll stay away from that. So my apologies up front to all the nerds and geeks that are on the call. But for the folks that actually are thinking about how can I incorporate quantum to solving real world problems, we believe this will be a very useful presentation for you. At least that's our goal, okay? So we're going to try to stay out of the quantum weeds. So David, we'll stay out of the quantum weeds. Okay, right? Good. Two mentions up front. So I want to thank D-Wave. They've been a great resource for us through this journey of almost 2 years as we had this notion that, wow, this work we're doing at the Port of LA at Pier 300 with our partner Phoenix, seems like there should be some processes here that we could solve better than we could with classical approaches with quantum. So D-Wave has been great. We developed a depth of bench internally on trying to bring to bear quantum expertise and matching that up with solving these problems. And first and foremost, trying to decide what those problems are that can be solved by quantum better than any other approach. And that in itself is a bit of a journey. We'll touch upon that. We're also going to, I'll lead out here, which I am, but I'll do a couple of slides and then turn it over to David. And then I'll come back on at the end on the wrap up. So we're going to pretty much go through the slides fairly quickly. David, we'll get to the meat of the process of how we identified the problems that had the most potential to be solved with quantum and how we approach that. And that I think is quite interesting, especially for those that are thinking about how do I make a quantum computer do things for me. Some backdrop here. So let's roll to the next slide, please, David. We're going to talk about something called HONE. And for those of you in the government space, yes, it's a backronym. Yes, we came up with the cool term HONE, and then we came up with, what does it mean? It means hyper optimized nodal efficiency engine. And what it is, it's an engine that is in use 24/7 at Pier 300 at the Port of LA. It is, it choreographs the operations at the port in essence. And as one can imagine, there are a lot of distinct and discrete processes that have to be analyzed and invoked daily. So we really did not know anything about port operations when we were asked to help out Phoenix on this. 18 months later, we had the first build of Hone up and running, and then we've continued to iterate and improve it over the last almost 18 months. So it's almost been 3 years it's been in use now. And then more recently, we implemented the first quantum process, and that's really going to be the meat and potatoes of the presentation. That process, how we identified it and how we attacked it, and what we're yielding from it, which is really, really quite amazing. So think about it this way. What Hone does is it's all about moving containers. You've seen them everywhere on trucks. It's in the news a lot these days because of the supply chain issues. And no, we did not cause any of those supply chain issues. We've actually helped, we like to believe, to mitigate those, which we have. We have the data for that. But these containers, they come in basically 20-foot or 40-foot lengths, and it's at a pier. It's all about minimizing the times you touch a container and move it. You want to, every time you move it, it costs money. So you want to get it off the ship, you want to get it positioned, staged, and you want to get it out of the port, whether by rail or by truck, as efficiently as possible. And that's really what Hone is all about. So let's see, there's one other key takeaway I want to throw out there up front. And so everyone be percolating this in the back of your mind as you're thinking about sort of the use cases that you may think quantum could help you with. And I'll tell you up front, all your assumptions are going to be wrong. All right. And when we embarked on this, the port operators, Phoenix, Savant X, and others, we all had preconceptions as to how we would go in and how we would optimize the port. And we were all wrong. And at the end of the day, it really was the data that drove the solutions. Okay. And that same data is what drove the first quantum process that we're going to talk about here today. So let's go ahead and move to the next slide if we could. Thank you, David. So 2 years ago at Pier 300, they were moving 1 million container lifts a year. So they were touching a container, moving it over 1 million times a year. They were running 5 trucks a minute through the yard on average, and they were pushing out 3 trains a day. Since then, with more efficient operations that have been driven by the Phoenix team and then emboldened by the technology such as Hone and other technologies, they've seen a minimum of 30% increase across the board on all these metrics. Next slide, please. And this is, I'm going to hand this over to David at this point, but I want to set the stage now. Everyone be thinking about this. So in 2018, here's the business proposition. In 2018, Pier 300 was purchased for $750 million, $750 million. In the last 4 years, it has achieved a greater than 30% increase in efficiency. And it was recently sold in January of this year. So think about what you could imagine that price might have been for which it was sold. And then we'll talk about that at the end. So just remember, it was bought in 2018 for $750 million, and it was sold this year in 2022. We'll do an office pool on that. So anyway, David, over to you.
Great. Thank you, Ed. Sure. I think it's useful for people to kind of know the geographic context for the port. Everybody talks about the port. You've seen it in the news a lot lately because of supply chain problems. But, what exactly, where is it and what does it look like? So here we have, California and Baja down here in Mexico and so on. Here's a close-up of the port. It's been variously called, the Port of LA commonly, but it was originally kind of called San Pedro, which is over here. But I think as the port grew in this direction towards Long Beach, it's now pretty much commonly called the Port of Long Beach. It's actually comprised of a number of piers, and we're only going to be talking about this pier here, but there are actually a number of, like there's a automated pier here, there's a military pier here, and there's other commercial piers. So trucks come in this way on the freeway system across here. You can see these black lines are the railroads that go to all the various piers. So let's go and take a look at the Pier 300 itself. So here's their railroad system here. They've got a little bit of a fan here so they can handle several railroad chains at once. The railroad yard is over here. Trucks come in this way, and they go into this thing called the fan over here, where they fan in and then they go and do various activities in the port. The ships, of course, come in here on the water, and they can have up to 3 ships at once that they're loading and unloading. The fan goes both ways, so there's an input fan here, and there's an output fan. And at the fan, there are fans out to 10 spots, so they can handle up to, gating in 10 trucks at a time. And there's no people at these kiosks. They're actually in this building here. As they come in, they're checked for various safety items, make sure they're licensed properly. Do they have a reason to be in the port? They should have an appointment, and so on. I'll talk more about appointments later. Mainly, we're going to be talking about this part of the port here, the so-called RTG yard. We'll get to that more later. Let's take a look at a vessel here. You've heard about them. They're big. Each of these containers are typically 40 feet long, 8 feet wide, and 8 feet tall. And there can be thousands on a ship. Ships come in various sizes. But because there are thousands on these ships, it can take usually 2 or 3 days to unload them. And not all the containers will be going to this port, but most of them, this pier, probably most of them will get off here. They also have to load on empties or exports with these large cranes. Really, the whole terminal is oriented around cranes. Here we have a picture of a large crane. These are the ship-to-shore cranes, and it's a little hard to guess the scale here, but these are very mammoth machines down here themselves, large tractor trailer things. You couldn't even see the size of a person here. So these are like several hundred feet tall. There's a man or a couple men up in this control unit here, and they have these large cables that yank the containers out of the ships, and they come down here, and then they're discharged into what are called bomb carts. They're just kind of dropped into these carts, and then they're sent in various places in the terminal. Might be going to rail. There could be refrigeration units called reefers. They could be going there, but most of them go to the RTG yard. Here's kind of an overall picture of Pier 300. Large cranes over here, ships come in here. This is the RTG yard itself, right in this area. You'll notice that these piles here are larger than these. That's because the RTG cranes can only straddle 6 across. So this distance from here to here is 6 containers. They're called RTGs because it's rubber tire gantry, and they basically move up and down the rows. So let me show you a row here, going back to the slide. This is a row, and it's actually, I think there's about 350 acres here, so this row is like almost a half a mile long. Another picture of the RTG, and you can see how it can be picking up containers, lifting them up to 5 stories high or thereabouts. They can be stacked up to 5 in one vertical direction. So just keeping track of where all this stuff is going is a problem. All of these cranes are instrumented. Here we have a top handler crane. It can only really work the top edge of a bay, but it can also lift these containers up essentially 5 stories. So they use GPS to determine where a container is being picked up and dropped off. And because there's a lot of metal here, like these big canyons of metal, the GPSs are working on Wi-Fi, and they don't really work that well. So the inventory is actually difficult to track in total. Generally, we know where a container is in terms of which bay it's in, but we don't always know where in that bay it might be. Here's another good picture of an RTG in operation. You can see that it's being lifted out of this bay here. That's a 40-foot container. Here's the rubber tire gantries. The controller of the crane is up here. And they may have to dig out containers because there's no guarantee that the container that the truck wants is readily available. So they may have to move containers around to get to the container of interest. This is the delivery lane right here. And you'll see the trucks come in here. They'll pull up. There's no truck here yet, but there will be. Or maybe they've taken this off a truck. But they'll dig out the container and then they'll drop it down onto the truck and the truck will drive away. So this little area here, or actually it's pretty large, 40 feet wide, and back is a bay, and this is another bay here, another bay here. So a row is made up of quite a few bays. Obviously, one of the problems we're really concerned with is reducing the amount of dig out that has to happen. In other words, trying to guarantee that the container that they want will be on the top. To work out a lot of these issues, we had to develop a set of KPIs, key performance indicators. That was developed in conjunction with the client. The things that are really important to them to track are like the number of deliveries a crane makes in a day, how idle or busy the crane is, and how far the cranes have to move every day. And then also importantly, how long trucks have to wait for a crane. There's a organization called the HTA, the Harbor Trucking Association, and they're a major stakeholder in how well the piers operate at the port. And they actually instrument some of their trucks randomly to track how long the trucks waited during that month time. And that feedback is given to the piers and they're kind of graded that way. So this screenshot here is actually a picture from a simulation that we wrote. We did a full digital twin of this part of the pier. And this is a package called Simio, was written in Simio. And a full up, visual simulation of the RTG yard. So you can see RTGs here rolling up and down. Unfortunately, I have video, but I didn't thought we should play it because it doesn't really translate too well over Zoom. But in the real sim, you'd see these cranes going up and down, trucks are coming in and being delivered and then exiting. You can see some trucks in waiting here at the rows. So why do we do a sim? I mean, it's an expensive proposition. It took many months to build this with a lot of client interfacing. But the main reason why we want to do sims is because we need to run experiments and find edge cases to our ideas about how to optimize the port. We want to predict basically what makes KPIs go up or down. And we might want to try out different ideas that you just could not do experimentally with a running pier. If you can imagine trying to imagine what the full inventory would look like and what would happen if it was full and what would happen if it's empty. Those are conditions which may never actually happen, but in the simulation you can easily create those situations and find out how your algorithms or potential algorithms work. So we did on the order of 100,000 different runs under different scenarios with this package. And we fully instrumented the simulation. This is the simulation again and the output from it. So you can see here, we're tracking things as much as each RTG and whether it was idle or busy, how many deliveries per hour it's making per day, the distance it moved, things like this. And then the scenarios that we're running. Here we're running a particular pointing system, assumption about how many trucks are not showing up, how full the yard is, which is down here, and how many appointments were kept and so on. So this was a pretty key instrument to determining what ideas worked and which didn't for optimizing the port. Let's see here. Now we're going to get down to the meat of the quantum part of this. Okay, so the simulation recorded a lot of different scenarios, and we could look and see what was important to optimize. And one of the things that came to the forefront was the appointing system for the trucks and how we're going to call the trucks up. I suppose most people don't know that if you are going to pick up a container with a truck at the port, you have to actually get an appointment to get it. So how do we make those appointments? We decided that we're going to bring the truck to the crane rather than the crane to the truck. When we first arrived on the scene at the port, primarily it looked like basically random containers were meeting random truck arrivals. And so we wanted to orchestrate that in a more orderly fashion. So we made sure that the truck appointments were made at the time that the crane would be in that area. However, because trucks have to deal with a number of things on their end of the business, traffic, weather, trying to find a chassis these days to even pick up their container could be an issue. They don't necessarily arrive at their appointment time. And so that appointment window could be anywhere from an hour before the appointment to an hour or two after the appointment. And so you could have large lines of trucks waiting for a container for a row. And so then the issue becomes, which truck do you call up when? And that's what this graph shows here. This is actually the classical solution versus the quantum solution that we built for this scenario. And then we have the trucks that are in the queue for this row. So this is taken from about 1 million different data points over a month's period of time and compared what did quantum do and what did classic do versus the number of feet that the crane had to move. And so you see here that we have 2 trucks in the queue, 3 trucks, 4 trucks, 5 trucks, 6, and so on. And actually it can go up to more than this, but we only showed 9 here. And you'll see that at first, if there's only 2 trucks in the queue, or if there's 1 or 0, it's not even on this graph. Obviously, those are trivial solutions. And even 2 trucks isn't too hard to do. And basically, classic and quantum move the crane on the average the same amount. With 3 trucks in the queue, the quantum is a little better than classic. But when you start to get to 4 and 5, you'll see that quickly the quantum solution outperforms the classic. This classic algorithm here is based on the greedy algorithm, which means that it's an easy thing to compute in real life. You just say, I'm going to go for the next closest container. And that's probably typically done in businesses now with this kind of problem. However, the quantum solution here running on the D-Wave is able to consider a lot more possibilities. And because of that, it could order the way that the trucks were called up and reduced over the average quite a bit in terms of the movement of the cranes. In fact, if you look out here, you'll see that even at 9 trucks, the quantum didn't move that much more than if there were 5 trucks on the average, even with that complexity. So the algorithm, which we're not going to talk about how we did it too much here, but I can say that, we wanted to build an algorithm using qubos that ran on the I think we're using the 2000Q. We wanted to be sure that we didn't write an algorithm that would run into certain issues on the D-Wave itself, like the dynamic range and things like that. And so this is basically an algorithm oriented around probabilities. What would happen if you're expecting trucks in, they're not in line yet, but what if they're coming? maybe that would bias you moving the crane one direction versus another and that sort of thing. So it's kind of a Markov chain kind of algorithm. And so that's the quantum algorithm that we've implemented. So there were a number of things that happened at the port with Hone, not just the quantum stuff, but all kinds of things. They bought some new cranes. They changed the way that they did the appointing. We had a thing where we could actually call the trucks up instead of having them in a FIFO line. We could call them up when we wanted to. Things like this. Overall, you can see the results here that happened before Hone and after Hone. And here's the deliveries per day, went from 60 to 97. Truck turn times dropped from 66, well, a little over an hour to a little under an hour. Crane utilization went up quite a bit, and the average crane distance moved went from 8,900 meters to 6,200 meters. Yeah, okay, so we did patent this. It's in patent pending status right now. And here you can see the first page of the patent. And I'm going to pass it back to Ed now.
As soon as I can find my unmute button. Yes, thank you, David. So to kind of come back around, when we embarked on this journey, the idea was get more containers through the pier without having to touch them as many times, right? Because every time you touch a container, it costs money. So by doing that, we did increase the terminal capacity. These were sort of our goals along the way here and at the onset, which gives you more, increases cargo flows. Hone itself, updated forecast. David talked about KPIs, identifying those, and then building to giving the visibility and the transparency that's required for those KPIs to track. And then as you try different processes to know if it's working or not and what you need to tweak. So this is definitely reduced cost. It's increased value at the port itself. The trucks are a big deal. The truckers, last thing you want to do is have truckers come into a pier and have to wait 2 or 3 hours to get a container. They want to be in and out of there in less than an hour, if at all possible. And through processes like with Hone and the discrete process, the quantum process that David just described, those all conspire to enable these faster truck turn times. And then there's VIP services that spin out of this as well. So just to kind of recap a little bit on this process, as I said at the beginning, let data drive what you do. Everyone's going to have preconceived notions. If only we could do this. If we can, and we fell victim of this, as I mentioned earlier, where we thought that our preconceived notions were way off, and really the data described this whole notion that if you don't have to move that RTG, that rubber-tired gantry crane around as much, then you're going to save money. And instead of ordering up 20 of those RTG cranes for a shift's work, if you only have to order 15, and you only have to have 15 cranes do the work of what normally would be 20 because you're doing it more intelligently, enabled with this sort of technology, that adds up to huge cost savings. Each one of those cranes, for context, employs about 25 people. So you can see where that'll quickly start adding up. I would also suggest that the quantum process that David just described here, we think we're seeing about a 3% of this overall increase at the port. We could probably attribute about 3%. So maybe the best way to think about quantum, because once you have tasted quantum and what it can do in terms of optimization on the D wave, it's tempting to look at every problem and say, gee, that's an optimization problem. When in fact, that not all problems are optimization problems, but the ones that are, there's huge opportunity to bring value into the equation here from a business standpoint and from an operation standpoint by the efficiencies derived through this optimization. So it's pretty exciting. In fact, it's very exciting. So if you think about it, it's kind of quantum whack-a-mole, at least for us in the context of Pier 300 and other ports. So So for instance, we can derive efficiencies here as David just described. And then there's a whole list of there's a pull down menu of other processes that we go to next. And as you gain efficiencies over here, then you'll find that this now becomes a problem over here. So that's how we approach this. It's very pragmatic. It's very real world. We're very excited to be at the cusp of this right now, because for so long, quantum has been largely limited to researchers, visionaries, and now you can actually take a quantum computer, the D-Wave computer, you can actually make it do something very useful, and with real KPIs associated with it, and that's exciting. Let's go ahead and go to that next slide, if we could, please, David. So back to the question I posed. Everyone is probably, I should have had already write this down on notes, but so in 2018, Pier 300 was purchased for $750 million. In 2022, in January of this year, the Pier was sold for $2.3 billion. And we're not claiming that Hone or that the quantum process we described here that delta was a result of that. We played a role in that, some small role in that, but it's been a fun journey, and now we're taking this technology and we're moving into other domains, and we've tasted the power of quantum, and we're very, very excited about it. So if we can, I guess we can roll to questions now, and thanks everyone. We tried to not compress a 10-minute presentation into 40 minutes, so hopefully we have some questions here that we can address.
Great. Thanks, Ed. Thanks, David. We actually have quite a few questions. We were able to answer some, but we will go through some of them now. Are further applications of your optimization system expected or intended for other American or external ports?
Yes. Yes, they are.
Okay. Does the solution use hybrid CQM or the older one? So a little bit about really how you did what you did.
I think Alex could answer that maybe, huh?
Oops, sorry. I was looking for my unmute button. Susan, can you repeat that one?
Oh, does the solution use hybrid CQM? I believe in this case, they were using the QPU directly and have not yet applied the hybrid solvers to this problem. Is that correct, David? That's right.
Mm-hmm.
I think you're also using the older 2000Q QPU, aren't you?
Yes, we're using the 2000Q, and we're formulating the QUBOs ourselves. And so we're going to the machine kind of in a raw fashion, I guess you'd have to say. We're not going through any of the solvers. That's right.
Okay. If possible, can you give an idea of the problem sizes you solved using quantum computing? Number of binary variables, number of constraints, etc.
That's a good question. The inventor of the algorithm is somewhere in the building here, but I'll try to answer this for him. His name is Michael Rogers, and he's our QUBO expert. And I've looked at a number of actually fairly often, the QUBOs that are sent as solutions. Now you have to understand that we're calling the D-Wave every 2 minutes for each row, and there's 12 rows. So we're calling the D-Wave every few seconds, actually. And this is done 18 hours every day, except Sunday. So the D-Wave is getting a pretty good workout. If there aren't many trucks waiting for a particular row, then the QUBOs are small. If they're, it goes up exponentially, essentially, because the histories that come down through the optimization of the QUBO basically follow every possible path or every possible order in which you could call up that set of trucks. So if there's 5 trucks waiting, then how many different ways can you call up the trucks? By factorial, right? So it can explode out of sight, and that's why people don't probably try to do these things classically. But it's fairly easy to do on the D-Wave.
Okay. Does the increase in crane usage cause a need for more scheduled or unscheduled service maintenance?
Oh, increasing crane, I'll take that one. Yes, the more you use them, more maintenance. And they have a tendency of breaking down at times too, especially if you're running them around a lot. It's better to keep them fairly stationary and work a pile that way.
Yeah, and they don't, they're made to go in a linear fashion, but if things happen, and they do, they may have to take a crane and wheel it around to another row, which is, you can imagine, quite hard on it. It's like putting your four-wheel drive and then doing tight turns. So it causes a lot of maintenance problems. In fact, one of our main concerns was not only reducing how much distance the cranes move, but what are the chances that the crane will have to be moved to a new row? And we try to avoid that.
Okay. Using Hone at the pier, how is the D-Wave services accessed and interfaced?
Ed, you want me to do that one, or do you want to?
Sure, yeah, that's fine.
Okay, so Hone runs in the Azure cloud. And so we replicate data out of the port and into Hone in its own little sandbox, if you will. And then in that process, all kinds of things are happening that are on triggers of various types. Things are happening every few seconds there. Some of the data tables are, 1 billion rows deep and things like this. The one part that's involved with the quantum is what we call mission sync, and that's what would be kiosks, for trucks, where they come in and sit at a podium and wait for their turn in like a herringbone fashion or something like that, where there is nobody who's in the front of the line. But because of the cost of doing kiosks and things, what was implemented during the last few years was what we call mission sync, and it's a phone app. And so when the trucks check in to the gate, they then go and they wait in line, and the truckers wait for the signal to come on their phone to say, now here's where your container is located. And it was before that, they got a ticket at the gate that told them where the container was. And some truck drivers would just plain drive right on up to their container row, skipping the queue, if you will. And so it was better to not tell them where the container was, it turns out, and have them wait in line and tell them right at the moment that we actually want them to come up where to go to. So during that process, the D-Wave is being called through an API, which is the one, if you use the D-Wave at all, any of the machines there, you call them through APIs. And so that's being done, like I said, every few seconds. The D-Wave then computes the answer for the QUBO and generally gets back to us somewhere between 5 seconds to 15 seconds. And then that builds a list of, this is the order I would do the containers in that are, for the trucks that are in line. So that list then can be used to actually decide which truck should go next. It's recomputed all the time. So it's a continuous process.
Okay. Adding on to that, for the layperson, what's the quick explanation for why it is so expensive in regard to cost every time a container is touched?
Labor and equipment cost. It boils down to that. It's until you experience to walk around the pier when it's actually in operation during just a normal shift, it's pretty amazing, the energy, because it's organized chaos, and it's amazing what they do. But trucks are running around, cranes are moving, and it's a huge overhead in terms of labor and the CapEx cost investment there. So just think about those huge cranes, just the ship to shore cranes to unload the ships. Those things are amazing. So yeah, it's a huge capital investment.
Referring to the graphic with the trucks in queue, what is the access Y with the number 50, 100, 150, 200, et cetera?
Okay, so
I think that's it, yeah.
This is the graph here. Yeah, this is the number of feet on average that were moved for all the movements across like 1 million different cases. So you can see here 50 feet. Now a bay is about 40 feet. So because of the way we appoint trucks. Hopefully there's several trucks getting containers out of the same bay so that hopefully the crane doesn't have to move at all, but pretty soon it's going to have to move to another bay. And the question is, do you want to move, north or south? And if you move north, then maybe there are more trucks that are going to be arrived to the south. So maybe you should have moved south and gotten that container. So it's an interesting optimization problem. And this is the number of feet on average on this axis.
Okay, wonderful project, great work. Could this project have been done with the same costs on an entirely classical solution, i.e. using classical optimization methods as opposed to Cubo?
That's how it started out, using classical.
Yeah, we use the greedy algorithm, which is this, line here. I think maybe the questioner was asking whether if you try to implement an optimization classically, what would happen? I think it would probably take too long for the purposes of the port, because right now the D wave actually solves the problem in less than a second, right? So the 5 to 15 seconds that we're waiting is mostly just bandwidth and queuing issues and things like this. So I think if you were trying to do it classically, think of this: you're trying to solve something every few seconds. I think it would take a large, server system, maybe even a supercomputer, to do that in any kind of reasonable time.
Okay, we have other questions that are kind of related. When building the quantum algorithm, what was the idea for the optimal solution to be? I guess you really didn't know what the optimal
It's a good
solution
question.
was, but
Yeah, do you want to try that one?
No, you've got your Mr. Peabody glasses on. I think you should do that one.
Okay, so yeah, so we thought about all the different things that we could do with a quantum computer at the port. That was the first thing, and this came rather later in the game, when we actually had an idea of what was happening at the port. You have to understand, when we first walked in there, we, like is typical of our things that our company gets involved in, we are not subject matter experts at first anyway. We kind of become more experts out over time, but at first we had no idea. And so just finding the potential places that we could apply quantum to was a process. And we eventually chose this one because this one is fairly discrete. We thought that the D wave response times matched the cadence of what's happening, with the trucks coming in, and so we chose it from that standpoint. And then our Cubo expert, Mr. Rogers, thought it was a problem that could be done on the D wave pretty readily, and would, for the annealing type quantum computers. I hope that answered the question.
yeah, actually, and there's one here that you sort of answered, but how was your experience with the research of the problem? How did you manage to understand the logistics of cranes and trucks inside the port? Did you work daily with the Pier?
Yes. Ed?
Yeah. Well, yes, you work with the Pier daily, and you go on site on occasion, but you work with the Pier. You look at the data daily, as David mentioned. We're replicating all the time. So you become very familiar with the data and the operations, what's going on.
And the simulation, to build the simulation, required understanding how the port worked, in fact, in fairly high detail. One of the interesting things about building a simulation is trying to figure out what's important to simulate. Because if you really look at the simulation, it looks very convincing visually. But, does it actually accelerate, decelerate, like how the cranes actually do? Well, probably not, because that we didn't feel was an important factor in the efficiency. A more important factor is the ability of the crane operator, because they can sit and try to get a container onto a truck for like half a minute, juggling it, trying to get it to fit. And so the tenth of a second that it takes to accelerate the crane to move to a new place is not a significant factor. So you have to pick out those things that you think are actually important.
Okay,
that-
we've got time. We've got 3 more questions. And I will send any questions we missed to David and Ed, and perhaps they can answer them via email. A couple of people have asked whether there is a paper on this or anything written up. Or do you plan to?
It's a good question. We have the, on this particular process, I guess the write-up is taking the form of a patent, a non-provisional patent, actually. So it'll be released whenever it gets released. I'm not sure of the timing when that'll come out.
Okay.
But as far as taking,
Apologies. Oh, sorry. Go
I
ahead.
was going to say, but as far as writing up a separate sort of paper on it, we don't have plans to do that currently.
Not on the quantum piece, but we do have a general white paper on Hone as a template. So
Okay.
there's that.
Apologies if missed in slide. What was the final calculation figures of cost savings, time savings, labor reduction, or however you were measuring? Okay.
This slide here, I think.
Yeah.
Mhm.
And at the highest level, the 30% across the board increase, and that's all the different factors we talked about, with just with Hone being a component of it, quantum being a subcomponent of it. They brought in new equipment, great management team at Phoenix. All these things conspired to really up to a greater than 30% increase in efficiencies.
And
Okay,
one thing I didn't talk about was the interface with the labor union. So you have the HTA Trucking Association as a stakeholder, you have the labor union as a stakeholder, then you have the operators of the port themselves as major stakeholders. And so I think the people who flipped the port, if you want to just say it that way, were very good at working with all those parties. And I think that did have an effect. It's an expensive, the labor union contracts on the West Coast are very expensive compared to, say, anywhere else in the world and even the East Coast. And so labor is a major consideration in anything you do at the pier. And it's not always easy to get a new idea implemented because they've been doing these processes for quite a while. And so there's a lot of tradition, a lot of tribal knowledge. And so like just putting in a passing lane, versus a FIFO lane can be a big change to implement.
Okay, and then the last one we have time for, are you planning further refinement to the algorithm through research, or is the algorithm pretty much mature?
Well, I'll say for this discrete one, I think it's pretty mature. What you, David?
Yeah, it's pretty mature. We've talked about, looking outside of the algorithm a little bit and maybe even optimizing that with the quantum. Like what happens should you really call up a truck if there's one truck waiting and you think that another truck, a better truck, might be arriving in the next few minutes, should you wait? Those kinds of things are maybe some areas that we could optimize more. But yeah, right now, the algorithm we have is pretty good.
Yeah, it's working well.
Mm-hmm.
Okay, well, with that, David and Ed, I'd like to thank you so much for your time and your preparation time for this. There was clearly a lot of interest in this topic. Again, this webinar is being recorded and will be posted to the D-Wave YouTube channel in the next day or so. And if there are questions we missed, we will try to get answers to you over email. So thank you all so much for attending. And as I said, we do these monthly pretty much, so on different topics. So please take a look at our website or the emails that we send. Thank you very much, everyone. Bye, Ed. Thanks, David.
Thank you, everyone.
Thank you, Susan.
Thanks.
Thank you.
Bye-bye.